Okay, so let's start our lecture today. Uh, so today will be on Zoom. Let me pull out the material of the book. So, okay, okay. Actually, let me oh shoot. Okay, so actually, let me just share the whiteboard. Okay, I think it's good. Okay, so I think I think last time I stopped at showing that so as long as you have a universal covering, then uh it is unique after a um equivalence class of homo. Actually, yeah, I want to show that it is the holomorphic universal covering is unique after a holomorphic equivalence relation. So okay, so what is the way that I'm trying to show this? Okay, so remember let me just copy the theorem here. Okay, so uh then we have theorem. Uh okay, so we have this theorem, the equivalence relation of universal uh wait. Okay, yeah. So I think this so okay. So let me yeah, so let me state here. Okay. Uh yeah, it's still loading here. I'm not sure. Oh, oh, okay. Okay, yeah. So we use this theorem. So first, we construct the universal covering, right? And then um and then okay. So yeah. So and then uh we let we let this big yeah. So we let the yeah we focus on the deck transmission group. Okay. So and then we say that there is um unique yeah. So here so yeah. Then there is a unique uh holomeric structure on this gamma. It is executed quotient out by the action of gamma. Yeah, executed quotient out by the by the orbit of this gamma. Okay, so then you will have this as the quotient space, and then this is a uh, biholomorphism. Okay, okay. So therefore, now we want to use this theorem. So um, okay. So now we want to use the theorem. Let me paste it. Uh, so it's here. Then let me paste it here. Okay. So we want to use this theorem. Okay. So why do we want to use this theorem? So um okay, so now so we first construct our x tilde, right? So we first construct this as x tilde from x. And then what we do is that um okay, hold on 1 second. Um uh, and then we focus on the space. Um okay, let's try this. So here we okay, so we show that this okay, we show that there is a biholomorphic map between the uh x and the uh what is it called? Let's call this x prime. Okay. So x prime, which is being defined as the um okay, so I want to be a little bit careful here. So I want to define this to be uh the deck transformation group of so here uh yeah, so I want to be a little bit careful here. So okay, so what do I want to show here? Okay, so okay, so this is the corollary that I'm trying to prove. Okay, so here this gamma is okay. So here there are different notions of gamma going on here. So in this statement of the corollary, this gamma is just a subgroup of pi one x x naught. Okay, so where the pi one x uh yeah, so where the pi one x x naught, this can be identified as uh the deck transformation group of the so what once we construct the universal covering, right? So remember this x tilde is like the universal covering. So once we do that, um this this gamma is a subgroup of can be regarded as the subgroup of the deck transformation group of this gamma. Okay. So uh and see. And then okay. So and then from the theorem from the theorem from the theorem 5.1.6. Okay. Um so we have constructed a quotient space from it. And then okay, so and then let's call this map. Okay, so let's call this map uh gammas of the variable gamma of the group gamma. Okay, so let's call that. Okay. Um which is the okay, so which is the deck transformation group of this gamma. Okay, so quotient by the okay, so it's like the x tilde quotient null by the or orbit of this deck transformation group of this gamma, particle gamma. And then okay, so then we can apply the uh yeah, and then there is a biholomorphism between this x prime and x. Okay, so it's a biholomorphism. Okay, then for this space, okay, so for this space, uh, no, so this is not actually yeah, so this is not actually really gamma. So maybe let's call this gammas of the deck. Okay. Okay. So just to know that it's actually quotient by the whole like the deck transformation group. Okay. Uh. Okay. So here. Uh. Okay. Oh wait. Okay. So here we let. Okay. So here we let the group gamma to be the subgroup of the deck transformation group of this gamma. So here we so okay, so we apply part B here. Okay, we apply part B to this this x prime. Okay, we apply the part B to here. So now we get um so now we let these to be the gammas of this gamma. Okay, and then we get a space uh let's say x hat, which is equal to uh x tilde quotient null by the group action of gamma. Okay, and then this is a uh, holomorphic covariance. Okay, so gamma hat actually. these are all holomorphic coverings. Holomorphic coverings. Okay. Uh, okay. So now by um, uh, Riemann surface. Wait. Okay. 5.1.4. Okay. Oh, okay. So here, okay, we use. Okay, so think by uh, okay. So now let's try to use this one. Okay. So this corollary says um that this okay. So that this um gamma from x hat to x and gamma check from x check to x be Riemann surface, and then you let the uh x naught to be in x, and then you let x naught hat to be gamma inverse of x naught. Okay. And then okay, so basically it says if you have the inclusion of the push forward of the fundamental group, then there is a unique commutative diagram of holomorphic mappings. Okay, so here basically you think of this x as the x prime here. Okay, okay, yes, uh, and then uh, okay, and then you think of uh, you think of the uh, okay, and then this because this x tilde is simply connected, it's a universal covering, so therefore the fundamental group is trivial. So therefore, the push forward map is trivially included in the push forward of this map. Okay, um, so therefore you get a okay, so therefore you get a unique commutative diagram. So uh, from uh, from x hat to x check. Oops. So okay, sorry. Is x check necessarily simply connected? Uh, Okay, so where did I construct this X check? Maps pi1 x hat x not hat isomorphically onto maps pi1 x hat x not hat isomorphically onto. Okay, okay, so maps pi1. Okay, so I want to show that it maps pi1 pi1 x hat x not hat isomorphically onto gamma. Okay, what is gamma? Gamma is a group of pi1 x not hat. Okay. So uh okay. Sorry, I'll double check at this point. Okay. I'll then and then uh I'll come back later. Okay. Sorry. Sorry about this. Okay.